Hello, in this lesson we are going to learn about confidence intervals. What's a confidence interval, you might ask? Well, I'm not going to tell you, well, not straight away. Anyway, I am going to take you through an example, and through that example you will learn all about them, more than you'd ever wanted to know about. Along the way, you will learn what a point estimate is, and then you will learn what an interval estimate is. And wrapped up with an interval estimate is the idea of a confidence interval. Finally, you'll also understand about what margin of error is all about. Okay, so here's the example that I promised. A random group of 200 secondary students were surveyed, and it was found that 72 students were in favour of banning energy drinks at schools. What is the 90% confidence interval for the proportion of all secondary students who would be in favour of such ban? And the answer, are you ready for it? Here is the answer. Here it comes. The answer is, it's blank. No, I will fill it in. The answer is 30.42%, comma, and 41.58%, close bracket. Okay, whenever we see such things like a bracket, number, comma, number, bracket, there are two possible ways of interpreting that in mathematics. That is either a coordinate or it is an interval. In this instance, it is an interval, in which case this is a lower bound and this is an upper bound. Okay, so this is interval notation. Oops, I was almost going to write interval in. This is an interval notation, and it means at least 32.42, and then everything in between, all the way up to 41.58%. What does it mean? Well, this is what it means. We are 90% confident that the population proportion which is P, is in this interval. So we will unpack all of this with some calculations, but really briefly, I'll zoom out and don't worry about slide 4 right now. What we're saying is, from this example here, we can work out the sample proportion, 72 out of 200. But what we don't have is the population proportion. It must exist, it'll be a number. We don't know what that number is. It is a fixed number. The population is all secondary students. So if all secondary students were surveyed and gave their opinion, we would be able to establish a specific, exact population proportion number, but we don't know it. What this does is it gives us an interval, a range of numbers from a particular lower bound to a particular upper bound, that we believe contains that fixed population proportion P. Our belief is demonstrated as a 90% confidence. This is not to say that there's a 90% probability that it's in here. That would be a slightly poor way of thinking about it, because the population proportion is a fixed number. It is either within this range of numbers or it's not in this range of numbers. But we can say that we have some confidence that it is in this between these two numbers. Now, slide 4 tries to break that down slightly. So here is P, the fixed population proportion. We don't know what it is, but let's just call it P. And let's just say we take 10 different samples of 200 secondary students. Then we know that every time we take a different sample, we will have a different, or potentially different, sample proportion. So these lines here, represent the different sample proportions and the interval where we think P might exist. Okay, from here to here, from here to here, from here to here, from here to here. Now, if we line them all up, so this one has a higher interval size than this one, for example. If we line them all up and then we say, well, where is P in this? and I draw a dotted line to show this is where P would be in these intervals. In this interval here, sample 1, P is just to the left of the middle. This one's almost bang on. This one's also almost bang on. This is slightly to the right. This one's quite much further to the right. Out of the 10 samples, in one of them, the population parameter is not at all in it. And for the other 9, it is. So that's where the 90% confidence comes from. Okay, hopefully as we unpack this, it'll be clearer and clearer. So we're going to break this down on how do we take this example and come up with this interval. And we'll do this on the next slide. Okay, so here's the breakdown. Step 1, find the point estimate. Here we go. First of all, work out the population, the sample the sample proportion. So the sample proportion is 72 out of 200. 72 had the matching attribute. 200 was the size of the sample. So p hat is 72 over 200, which as a decimal is 0.36. Now here's the key thing to take down. You might want to pause the video and write this into your theory books. The point estimate serves as an estimation of the population proportion. That's all point estimate means. So we don't have the population proportion. All we have in front of us is the sample we took. And so we say, well, our sample proportion was 0.36. So we're going to estimate that that's the population proportion as well. It's only a single point of reference though. So that's why it's called a point estimate, because it comes from a single value as opposed to maybe averaging out 10 samples or something like that. So it's a point estimate. Okay, so there are some good things and bad things about using a point estimate. And I've got them on this slide too. You might want to write these into your summary books as well. Number 1, pretty obviously, it is quick to calculate. We just did it in about 2 seconds. Number 2, well, we're not going to go out and do, say, 10 samples of 200 students. That might take too long. We're certainly not going to be able to do a census where we look at every single secondary student and ask them the question. It'd be nice if we could. So effectively, it's the only data we've got. So therefore, it's a good thing. It's a point estimate. It's better than nothing. However, as I sort of said before, every sample has a different p hat, right? Every sample has a different point sample proportion. And therefore, it will have a different point estimate for the population. So that's the big downside of it. So what we do is we don't have a solution, but we have a little bit more of a nuanced piece of information we can figure out. And that's where we go to step 2, work out an interval estimate. Now, as I said in the previous slide, and we are using the phrase interval as in a range of numbers from a lowest to a highest. It's a set of numbers from a particular value to another value. So what we're going to do is we're going to use this p hat that we worked out to find an interval, a range of values, in which we can be reasonably certain that the population proportion exists. Okay, so we would be hoping that the population proportion will be somewhere in that interval. And by hope and reasonableness, we are talking about confidence. Okay, so when I talked about a 90% confidence, that's what we're talking about. And this, the level of confidence, is called a confidence interval. Now, throughout this example, we are going to be using a 90% confidence. But you'll see as we go through how we work it out based on 90% could certainly apply to a 95% confidence interval or a 99% confidence interval or a 50% confidence interval if you wanted to. Normally, you try to stick for something a bit higher than 50% confidence, but nevertheless, any interval could be calculated with a particular confidence to it. It's just up to you to decide what level of confidence you're going to have. Okay, so just to remind you, I'll zoom right out so you can see all 4 at once now. Don't forget to pause any way along and just write some notes if you need to. 90% confidence interval means that 90% of intervals are likely to contain the actual population proportion. That's what it means. The higher the confidence percentage, the wider the interval. In other words, if I go for a 99% confidence, I can do that with my sample, but you'll find that the interval is wider. So at the moment, this 90% confidence interval from 30 to roughly 42 is about 12%. Okay. in a 95% confidence interval, instead of being 12% wide, it might be 20% wide. Or if we go to 50%, we might find it's narrower. But then again, we're only saying that it's going to be in there with a 50% confidence. So it's all about getting the balance right, I guess. Okay, let's move on. This is the formula. I've got some good news and some bad news. Good news is I'm not going to explain the formula to you. It's not really bad news. The other news is that why does this formula exist? I will do so in a different video. Okay, so right now I'm asking you to take it on trust that this formula will work. So what have we got here? We have got the lower bound is given by taking the sample proportion and subtracting z multiplied by this thing under the square root sign, which should look reasonably familiar to you. It's the standard deviation that we looked at before of a population based on a sample. And then the other side, the other interval, is p hat plus z multiplied by this big old number here. Okay, so this again is the lower bound, this again is the upper bound. You can see that if I've got p hat minus this and p hat plus this, we are centering around p hat. So p hat is the middle, and we've got a symmetrical range around p hat. Let's have a look at this in action. I'm going to zoom out, and I'm going to fix that in place so that you can see it. And I am going to do some calculations. So for our example, the first thing we need to do, you can see in the formula, we've got p hat, which we kind of know already, n, which we know is 200. So the main thing that's missing from this formula is z, right? So what does it mean to work out the z value? What we do to work out the z value is we take our confidence interval, which if you remember was a 90% confidence. So if I draw a normal distribution graph with our classic old mean of 0, standard deviation of 1 unit apart, these are our z values, then if I take a symmetrical chunk either side of the middle and say that's 90%, then if I can work out the z values either side, then that will give me the 90% proportion. I'll give me my z value, right? So all you have to do is remember that if I'm taking the middle 90%, the tails at the end, these things here, which are going to be equal, is going to be 5% each. So you take the difference between 100% and the chunk in the middle, and then you're left with the end tails of 5% in this case. If I was doing a 95% confidence, then there would be 2.5% on either side. If I was doing 99% confidence, there would be 0.5% on either side. So what we end up doing is we take the inverse norm and we put in our three values. Now, you can put 0.05 in for the 5% and then 0.1. And if I do that on my calculator, I will get manual probability or statistics. Why not do that? Statistics. And then we will go to distributions. It's the same thing, statistics or probability for this particular thing. And I'm going to go to inverse normal, which is number 3. And I say the area I'm looking for is 0.05. Keep the mean and the standard deviation the same. Press return. I get minus 1.644. Now, I guess the key thing just to keep in mind here is that actually we don't care about the sign, because you can see that we're effectively having the minus here. Sorry, you can't see my screen. Effectively, we're having the minus here already included, and then we've got the plus here with p hat being in the middle. So effectively, this is kind of like the p hat, and we're just looking at the z values either side. I'm not too sure how to say this really more clearly than this. We could put absolute value signs around the outside if you want to say take off the sign, or SIGN sign, or instead you could put in 0.95. So you're always looking at the right-hand side value of Z. Okay, so again, 100% is the whole thing. Take away 0.05, and I'd be left with 0.95. And that'll always give you the positive value as well. So whatever you think you'd be more safely able to remember, either put it in as you kind of see the area, 0.05, but ignore the negative, or put it in, but always take the right-hand side value. So 100% minus the 5% is 0.95. And it gives me, try that again. 0.95, and you can see it gives me exactly the same value except without the negative. Okay, so whatever floats your boat. So I'm going to write 1.645 down, but or 6449 down actually. Should do it to 4 decimal places, but we're going to be using that full value as we go along. So 1.6449 is our Z value. And now that we've got our Z value, we can put it all together. The p-hat value we already knew, it's 0.36. And the n value we already knew, it's 200. Okay, so we've got all three parts. So now we can work out this interval. And what I'm going to do is I'm just going to work out this little bit separately just to make it a little bit more straightforward for us and then move on from there. So what have we got? We've got Z, 1.6449, multiplied by the square root. Again, this is where it looks harder than it really is. 0.36 is p-hat. 1 minus p-hat is just the opposite value to make it up to 1, so 0.64, all over 200. So that's that done, and that is equal to 1.6449. So I'm going to use this value rather than just the 4 decimal place version, so it's as accurate as possible, multiplied by control square x squared to get the square root, control divided by to get the fraction, 0.36 multiplied by 0.64 all over 200 is equal to 0.0558. I'm just going to write this down and then I'll flick back over. 0.0558, like so. There we go. So that is now that value. So therefore we have the following. We have on the left-hand side, so the lower bound is p-hat minus 0.0558, and the upper bound is p-hat plus 0.0558, and these two values are, again, using as many decimal places as possible. So 0.36 is our p-hat value, and I'm going to subtract that, and I get 0.3042. I'm just writing it down and then I'll come back to you. And then I'm going to, again, just be a little bit smart and go use my up arrow key to grab that value again and then change it to a plus. And I get my upper bound value of 0.4158. I'll flick over now so you can see I've written those down. And so what does that give us? A 90% confidence interval of, I can write it as a decimal, 0.3042, 0.4158, or I can write it as a percentage, 30.42% to 41.58%. And that is my confidence interval, and you can see that that matches what I gave you in the first slide, 30.42 to 41.58. So that is how we work out a confidence interval. I could stop the video there, and that's basically it. However, I want to show you a couple of effects when we change certain parameters to see what the effect is on the confidence interval. You can see from these 4 slides here, in part A, instead of going 72 out of 200, I'm going to go for the extreme value of 190 out of 200. In part B, you can see that I've kept the proportion the same. Instead of 72, it's 720, and instead of 200, it's 2000. I've kept the confidence intervals exactly the same. Okay, this, believe it or not, won't take too long, and I'll explain why as we go along. First of all, what is p hat? Well, if it's 190 out of 200, that probably doesn't require too much brain power to work out that the sample proportion and hence the point estimate is 0.95. Great. The Z value, well, it's still a 90% confidence interval, right? So that means that my Z value is going to be unchanged. It's still going to be, I'll just do it to 2 decimal places to make it a bit faster because I'm going to use all decimal places from the calculator. So the Z value is 1.65. It doesn't change. So once you start knowing your Z values, you're kind of okay. If you think about it, there are certain confidence intervals that you already know the Z values for. If you think about the 68, 95, 99.7 rule. Okay, so what does that mean then? We will have a calculation of 1.65. So this variation from the point estimate, p hat, 1.65 multiplied by the square root of 0.95 now instead of 0.36 multiplied by 0.05 all over 200. And if we do that on our calculator, we can do it actually fairly quickly. I have done it before, of course, but just to show you how easy it is, I can just press enter to get the old one. And now I'm just going to change these values to 0.95 and 0.05. So these should always add up to 100, also 1. And we can see that we have got a value of 0.0253. That is our new variation from the middle of p hat. Okay, so what does that mean then? The confidence interval, and I'm going to do it in one line rather than the way I did it before, but you can do it the way I did it before though. The confidence interval is going to be 0.95 p hat minus this variation, which is 0.0253, to 0.95 plus 0.0253. And if I simplify that now, I'll have a new 90% confidence interval. I'll just go straight to percentages and I won't do the calculator part of it. I'm sure you can work that out if you need to, of 92.47% to 97.53%. And so you can see we've got an interval length of roughly 5% there. Secondly, part B, we've got 720 out of 2,000. Now, I hope you can see that if you did it on your calculator, that would be a sample proportion and hence a point estimate of 0.36, exactly the same as we had in the original example. Okay, so Z, hopefully unsurprising, is still 1.65. Okay, there's still no change to this value because that value will only change if we change the confidence level. Okay, we're still looking at 90% confidence. It's still going to give us a Z value of 1.65. So let's work out what that difference from the p hat value is then. So we've got 1.65 multiplied by the square root of, in this case, 0.36 multiplied by 0.64, all over, not 200 this time, but all over 2,000. Now have a think about what that might mean. If I've got effectively, the same calculation as I did in the original example, except that my denominator here is 2,000 instead of 200, what does it mean about this value here? If this is bigger, if the denominator is bigger, this fraction is going to be smaller, and therefore the square root's going to be smaller, and so we are going to get a smaller value here overall. I can tell you, to be more precise, that the value is going to be 0.0177. Again, just saving my calculator usage by just telling you what it is. Okay, so what's the 90% confidence interval in this instance then? Well, it's going to be 0.36 minus 0.0177, comma, 0.36 plus 0.0177. which in percentage terms, you don't have to keep it as percentages, just PS. I just kind of like to see it as percentages. 34.23% to 37.8%. How good is that? So a video ago or in class, we talked about what's the point in having a larger sample size. Well, here we can sort of see it coming to roost. With a bigger sample size like 2000, even though the proportion was the same, we have now got an interval, a confidence interval that is just a 3, maybe 4% difference. So it's getting better and better and better as we increase our sample size. This is a main reason why we would want a large sample. So in summary, strong matches or rejections against the criteria. Our criteria was that energy drinks should be banned, or a student that thinks energy drinks should be banned. If nearly everyone thinks energy drinks should be banned, then we can see our confidence interval shrinks, which is a good thing. Okay, it's a smaller range of values. It would also be true, of course, I said strong match or rejection. If that was the reverse, if it was 10 out of 200 students think that energy drinks should be banned, then that would be 0.05, but then that would be 0.95. Okay, so if it was the opposite, you would still get this strong effect, in which case you would have this kind of thing happening here. But the other thing but even more importantly, I think, if you take a large enough sample, then you are going to minimize this value here, which means that you are going to be shrinking your the length of your confidence interval as well. Okay, so these two things massively help. Last thing to look at, margin of error. I only need one slide to describe the margin of error. M is equal to what? Believe it or not, you already know. M is equal to Z multiplied by the square root of P hat. Is this looking familiar? Can you fill it in before I finish? P hat over 1 minus P hat over N. In other words, the margin of error is the bit that separates out the interval from P hat. So in our examples, when I was trying to work this out, I'll do it in different colors so you can see what I'm doing here. This bit here was simply M. Okay, and I can go back and I can write it all the way along. And instead of talking about that bit which separates out p hat, I can now talk about it as the margin of error. Okay, so what does that mean? So it's the bit that separates out the interval from p hat. So from the original example, we remember where we had a margin of error of 5.6% or 0.056. What we can talk about is that if we were reporting back to the press or something like that, we could say that 36% of all students plus or minus 5 to 6% error. In other words, 36 plus or minus about 6 with confidence of 90%. Okay, I'll just say that bit more verbally. I was writing as I was going along. So you could say something along the lines of, I think that there's about 36% plus or minus 5.6% of all students think that energy drinks should be banned. And I can say that with a confidence of 90%. That's what all of that means when you see it in a press statement. Okay? Keep that in mind. Okay, one last thing, very, very last thing, and that is I just wanted to show you that here it is on your information sheet. You've got this being the lower bound, this being the upper bound, this being the margin of error, and in case you forget how to work out the Z value in your blind panic in the middle of an exam, it gives you the Z value for 95%. So if the question is, what is the 95% confidence interval? You can skip all of that little bit of the step that works out the Z value, and you can straight away just put in Z equals 1.96, which is very cool. One last thing. I think this is my third one lasting, but anyway, in a separate video, I've already promised you that I will show you how this formula, sorry, went too far, how this formula comes to be. It won't be a very long video, and it's actually not too hard to figure out, and it's quite interesting. So look out for that one. But the other video I'm going to do is I'm going to show you how in the calculator section you can do all of this, get all of this information out, do all of this step in about 2 minutes on your calculator, less than 2 minutes, which is really good. So why would you do all this if your calculator worked it out for you? Number one, if you don't know how to do this, then you won't understand what your calculator is telling you. And number two, purely mercenary, from purely mercenary reasons, if you have a question that's worth 3 or 4 marks and you use your calculator to work out the confidence interval, then you'll get 1 out of 4. So you need to know how to do it manually so that you can demonstrate understanding of the process to the marker. That's it for this video.